Okay, let's go through at least one more example. So we've got 4 resistors connected in kind of an odd shape. One advantage to doing the Kirchhoff's laws over the equivalent circuit is sometimes if you look at this circuit, you don't know what the connections are. If you do Kirchhoff's laws, you don't have to know what the connections are, so there is an advantage. So let's label each of our currents in our circuit. So let's put current I1 as the current going through the 6 ohm resistor. We might call that R1 if we wanted to. Then current I1 comes to this junction. You see it has 3 places it can split. Some of it can go down through the 4 ohm resistor. We'll call that I2. Some of it can go down through the 48 ohm resistor. We'll call that I3. And some can go through the 16 ohm resistor. We'll call that I4. Okay, so there's our 4 currents with one junction indicated. We also want to indicate our loops. I think before we do that, why don't we put our pluses and our minuses on our resistors? Okay, so there's our diagram with all of our currents. Next, let's identify each of our loops. To identify our loops, I'm just going to do it over 3 diagrams. I'm afraid it'll get too messy if I put them all on the single diagram. Okay, loop 1 I'm going to take on the leftmost part. So I'm going to call this loop 1. Loop 1. So loop 1 comes out of the 12-volt battery through the 6 ohm and through the 4 arm. For my loop 2, I'm going to choose to go from the 12-volt battery through the 6 ohm, through the 48 ohm, and back around. So that's a valid loop to pick as well. So there's my loop 2. Remember, there are lots of different ways to pick loops. Sometimes with a little bit of foresight, you can make choices that just make the algebra more simple. And then for my loop 3, I'm going to take the whole outer loop. So I go through the 12-volt battery, the 6 and 16 ohm resistors, loop 3. So we've got our currents done, we've got our loops done. Let's write our Kirchhoff's laws. So for Kirchhoff's law, current law, we know that for the junction we indicated, the current in is I1. That's equal to the net current out, which is the sum of I2, I3, and I4. Next, let's write down our loop rules. We'll do loop 1 first. So for loop 1, we've got a potential increase due to the battery, plus 12 volts. We've got a potential drop across the 6 ohm resistor because our loop goes from plus to minus. So we've got minus 6 times I1. I'm dropping my units here. You don't have to if you prefer to keep them in. And then I've got a drop as I go through the 4 ohm resistor, minus 4 I2, and that's going to be equal to 0. I'll write my equation for loop 2. So for loop 2, I've got a potential increase due to the battery. I've got a drop across the 6 ohm resistor. And I've got a drop over the 48 ohm resistor because our loop goes from plus to minus. And here, of course, I'm using Ohm's law that says V equals IR. Last, I'll do my loop 3. So loop 3 is my 12-volt battery supplying potential. I've got a drop across the 6 ohm resistor. Then I've got a drop over the 16 ohm resistor because my loop goes from positive to negative, minus 16 I4. Okay, I've got 1, 2, 3, 4 equations. I've got 1, 2, 3, 4 unknowns. So now we just have to solve the problem. I'm going to take each of my 3 loops and I'm going to solve the currents for I2, I3, and I4. Then I'm going to plug them into my current law. So let's start with loop 2. So 12 minus 6I1 equals 4I2. That means 4I2 is equal to 12 minus 6I1. So I2 is 12 divided by 4, that's 3, minus 6 over 4, that's 1.5 I1. Okay, loop 2 is next. I've got 48I3 equals 12 minus 6I1. So I3 is 12 over 48, and that's 0.25, minus 6 over 48, 0.125, times I1. And then for my loop 3, 16 times I4 is equal to 12 minus 6 times I1. So I4 is 12 over 16, that's 0.75, minus 6 over 16, that's 0.375, times I1. Now I'm going to plug each of these, I2, 3, and 4, into my expression for my current law. Let's keep going with our algebra then. So I1 is equal to I2, which is 3 minus 5I1, plus I3, which is 0.25 minus 0.125 times I1, plus I4, which is 0.75 minus 0.375 I1. There, just managed to squeeze it all in there. So I1 is equal to 3 plus 0.25 plus 0.75, that's 4, minus 1.25 minus 0.125 minus 0.375, that's 2. So I1 is equal to 4 minus 2I1, which means that 4 is equal to 3 times I1. So I1 is 4 over 3, or 1.33 amps. Okay, there's our I1. Next we can find our I2. I2 is 3 minus 1.5 times I1. So I2 is equal to 1 amp. Next we can find our I3, 0.25 minus 0.125 times 1.33. So I3 is 0.0833 amps. And then on loop 4, I4 is 0.75 minus 0.375 times I1, which is 1.33 amps, to give us 0.250 amps. Okay, so there's the currents through each of our resistors. We're also asked for the potentials. So we'll take our potential, or we'll take our currents and our resistances, and on the next slide we'll find the potentials. So now let's put our answer together nice and neat. Our 6 ohm resistor, that's got current I1 equals 1.33 amps, and it's got potential equals I times R, 1.33 times 6, 7.98 volts. I guess if I didn't round off my 1.33, that would go right to 8 volts, 7.98 volts. With problems like this, if you round off in your steps, you're going to get a little bit of rounding error. In our 4 ohm resistor, we've got that's current I2. I2 is equal to 1 amp. V2 is the current times the resistance, going to give us 4 volts. For our 48 ohm resistor, I3 is equal to 0.0833 amps. Our potential V3 is the current times the resistance, 3.999, or 4 volts. And our last resistor, the 16 ohm, that had current that we called I4, 0.250 amps. And the potential across it is current times resistance, so 4 volts. One thing that I find a little bit interesting about this result is if you didn't know how these resistors were connected, this answer might give you a little bit of insight. See how the potentials across the 16, the 48, and the 4 are all equal? Those 3 resistors are actually connected in parallel. I've got a FET simulation that I'll show you on the next couple of slides that talk about this. So I've got a FET simulation here just to run us through our answers and confirm that they all match. So we see the current running through. The current through our main branch through the 6 ohm resistor is 1.33. Through the 4 ohm resistor is 1 amp. Through the 48 ohm resistor is 0.08. Through the 16 ohm resistor is 0.25. Then we can measure our potentials as well, and they match what we measured. One thing you might think about with those currents, maybe you noticed, is that the current through the 4 ohm resistance was the biggest. The current through the 48 ohm was the smallest, and the current through the 16 ohm was in between those two. That makes sense when we think about our definition of resistance. It's resistance to current flow. So you get more current going through branches with less resistance. Okay, we'll look at on the next slide about how those three resistors, the 4, the 48, and the 16, are in parallel and how you can see that connection. So now, I said as we worked through the problem that the 16, 48, and 4 ohm resistors were all connected in parallel. I'm going to run through a FET simulation now that also shows how they're in parallel. So here's the original setup, and I'm putting the ammeter on to show the currents. If things are in parallel, you're used to seeing them a certain way in a circuit diagram. So what I'm going to do is just change the circuit a bit to add little pieces of wire and rearrange my circuit so that it looks more like the traditional one. Remember, little pieces of wire don't have any resistance, so you can make wires longer or shorter, or you can bend them into different shapes, so you can move them around and stuff like that because it doesn't fundamentally change the circuit because they don't have any resistance. There's no potential drop across them. So rather than have them all meet at a single point, I put in some extra little bits of wire and I just spread out that meeting point. See that didn't change any of the currents. So I've still got the same circuit. Now I'm going to do the same thing. First, I'm just going to move that 16 ohm resistor so that it looks the way it does when we're in a regular parallel connection. Now the simulation's a little bit fussy to work with, so I've got to break things apart and line them up. I'll cut that wire there. I'll turn it vertical, and then I'll just put the wire back. Okay, so we still have the same circuit. I just moved that resistor on a bit. Okay, now I'm going to take my 48 ohm resistor and the little snippet right down there in the corner, I'm just going to add a couple pieces of wire down there. Not going to change anything about the circuit because it's just pieces of wire with absolutely no resistance. Put in another little snip of wire. Okay, now those are hooked up. This looks a little bit more like the traditional parallel connection. So hopefully you can see that. Again, I just want to line it up so it looks a bit more vertical. You don't have to do that, but that's what it looked like in the previous pictures. Okay, last one I have to do is the bottom left-hand corner. I'm going to snip that open and I'm going to put in some little pieces of wire there. Okay, so just by putting in the pieces of wire, it doesn't change anything about the connection. Okay, it's not all perfectly lined up, but hopefully you can see now that this looks like the traditional parallel circuit, and we have all the same currents, so those two circuits are equivalent. Okay, and we can measure those potentials. I got my 4 volts there, 4 volts here, and 4 volts here. So we could have done this problem using equivalent circuits, where first we connected the 16, 48, and 4 with a parallel connection.